Good morning, good afternoon. Welcome to a presentation called Urban.Ai that is about the creation of sustainable urban fabric with the use of artificial intelligence. And this is a final presentation for the digital tools for computer vision and data encoding seminar. And the students are Joao, Silva, and myself, Bodenbender. The framework of the project is about the concept of machine learning applied in urban design. And we understand that in order to best accommodate rapid urbanization, designers may utilize quantitative tools in order to make informed decisions in real time. We also understood that computational workflows has proven to be a really successful approach, dealing with the building scale, but really challenging at the moment applied to urban scale. That's our focus in how we can actually test and develop a new approach using machine learning applied to a more sustainable workflows for the urban design. On our case, then we started doing the research of state of the art, and we came across this paper from KPF that talk about how can generate 1,000 master plans, a framework for computational urban design that talks about how the importance of the city block as a minimum building block for cities, and how it's important for us as a designer to introduce sustainable metrics on real-time design workflows in order to build better cities. Also talk about the concept of the traditional process versus the computational process, and how now we added on top of this, how now we can introduce a machine learning process on top of it that help us now to deal with all of those processes that are really time-consuming and complex to calculate it. And by the use of machine learning, we can fast-track and open new opportunities. By this, then we jump into a pseudocode, and we define a series of steps that started with first defining the metrics and measurables for an urban block. Then we did geometry generation using Grasshopper. After we got a defined block, then we use Cojones map to be able to do the dataset creation. After that, we train a machine learning process using regression, and after that, we develop our own app where we implemented the trained machine learning model. On a parameter space, here's where we define it. What is the ins, the parameter space, and the outs of a process? We then set up a series of dimensional data as a parameters in, like in this case, plot width, depth, heights, and so on. Using these initial outputs, then we actually generate the blocks and create the initial calculations like build volume, area, plots, and so on. And then we define the outputs, meaning what are these complex calculations we want to measure on each of the blocks, and later on when you apply to machine learning. In this case, sun hours, green comfort, and energy self-sufficient. So after defining this, then we move into the geometry creation space. For this, we created a Grasshopper component that takes care of the entire process, and for each block, it takes about a minute to run. The output of this is a single urban block. So what we did is we connected this Grasshopper script with WALAC, that is a genetic optimization algorithm, to then generate 4 different blocks. What we asked WALAC to do is to find us 2 of them as the most optimum performance ones. You can see the ones on the left and top. And then we also choose the ones that are the worst performing ones. The reason we did this is because then we took these 4 initial seeds and we fit it into a Cojones map in order to create a data generation. This allows us to create 3,150 different samples, all of them across the maximum variation of the range. As you can see here, this is the displacement of the Cojones map. And then in this case, we not just plotted on the X and the Y axis, but also we added the radiation values on the Z axis in order to understand the performance of each one of these examples. The resultant of this is all of these different block iterations, but most importantly for us is the data set we created from it. And as you can see here is 3,150 generations across 16 different columns. This is a CSV we then use for a further PC analysis that Joao is going to talk about it.
Yeah, so once we had our features collected, it was very important to get a deeper understanding of how they correlated with our prediction targets. And we were looking for the ones that were very important to explain the variance in our data sets, but also the ones that we could actually drop. And for that, we used a range of different tools for data analysis, bivariate distributions, correlation coefficients, principal component analysis, and eigenvalues. And on the next slide, you'll see that the bivariate distribution gave us a broad understanding of how the metrics correlated. But to really grasp what was happening, we plotted a Pearson correlation heat map. And so on the next slide, you see that it was quite obvious that while some metrics were extremely important to our predicted targets, like building volume or gross area, others were quite irrelevant, like plot count. And we also noticed that some had inverse symmetries, like building area and green area. So probably one of those could be dropped. And on the next slide, you see that we went for a blind plot of the PCAs. And here it was clear but we only really needed 5 or 6 features to get a good picture of our data. So in the next slide, the biplot helped us understand in a 2-dimensional space what forces were really driving the PCA. And we could see 4 major branches with some metrics overlap, which could be maybe disregarded. And on the next slide, once we put all this information into a heat map, we started to understand the hierarchical relationship between these features and the PCAs. So finally, in the next slide, by the end of this process, we were left with 6 major features that were really essential for accurate prediction of the three targets.
After defining and running the PCA and defining the features we need to implement, we move into the machine learning process. For this, we started understanding which machine learning process will be the appropriate based on the data. We then finally arrived at the conclusion that we need to go through a supervised learning and then use regression model on a deep learning approach in order to tackle a problem. That's why we arrived to the conclusion that we're implementing a linear regression model to classify to predict the building. In this, we went through multiple iterations and started with a really complex architecture, started reducing later to a much simple and less dense layer. And as you can see here, this is the first attempt to actually for a single prediction, where we're trying to select certain features and predict the energy balance column. As you can see, we chose a 5-layer architecture, started with a 32 neural layer, and ended up with a single linear layer at the end. We implemented the Adam compiler, and we used the mean square error as a loss. After multiple iterations, we arrived to a validation loss of 0.0057. That is the best performance we have. As also we can see here, the model is performing well without overfitting. And when we plot the plot prediction comparisons with existing values versus the truth, we can see that the predictions are quite accurate. After we arrived to this conclusion, now we move to the second attempt that is actually started trying to predict the other columns, in this case, radiation. We also obtained really similar results with a slightly less accuracy, in this case 0.13, but we're still really happy with the results and the model was generalizing really well. After we understood that the columns are predicting well based on the features we selected, then we attempt the last attempt, that is a multi-prediction approach. We're trying to predict 3 different values at the same time, radiation, green, and energy. As you can see here, the model started being slightly overfitted, but we got a validation loss of 0.0981. We're still really happy with the results, and when we plot the prediction comparisons, we can see that the model is generalizing really well and without many outliers on the sample. So after we performed this, the question was for us, how can now we implement this back into the designer space? For this, we use hops. So we train a model locally, and then we connect it together with Visual Studio and hops. That is a Grasshopper component that allows us to run GPython on the outside, allow us to actually run the predictions live on a design environment. Then we package this into our Urban Design app natively on Grasshopper. And as you can see here, this is where now the designer can interact with the different inputs as we selected. And now the machine learning algorithm connected through hops is real-time predicting the values that before on a computational design process, it could take up to a minute on each prediction. So now we'll pass it to Joao.
Yeah, so once we had a very positive response in terms of predictions for our generated data set, and we had all this live connection established in Grasshopper, we wanted to really bite the challenge of testing this model with existing real-life urban blocks that we could just pick from OpenStreetMaps. We really focused on the question of how to deploy our model for the open source community, democratizing the use of more complex sustainability tools for the broader use. So in the next slide, you'll see that we started to do some trials. We first picked a block in Lisbon that is very close to our trained data set, similar shape, similar size, a uniform building footprint distribution. And as you can see here, we got pretty good results in all 3 predictions, although energy balance, which was the least correlated in our matrices, was slightly behind. But then on the next slide, you see that we gradually stepped away from similar blocks. In this case, New York starts to have a different building footprint and the values went down slightly. And on the next slide, you see, okay, now we move all the way away from our data set and we pick this London block, extremely different and quite unpredictable to our model. And as expected, the prediction actually plummeted. And we did, on the next slide, we did the same thing, but to the other extreme. We took a very small block from Paris, medieval era, and with a compact footprint and scarce green spaces. And as expected, the values were quite low. So then, we started to really reflect on this task of how this task could actually be accomplished. So on the one hand, expecting to train an OSM blocks from the get-go is a hard strategy, since it's quite difficult to automate the geometrical cleaning of the blocks. Now, another strategy could be to approximate OSM geometries with our data generator, perhaps increasing the data set in terms of shape and proportions, but also building parallel regressions that would translate values from different scales and different locations. But to be honest, by the end of the process, we were very excited with the strategy that was more about decoding the information of the OSM type file, from where we could extract the polylines, the heights, and the location information, essentially taking geometry entirely out of the picture and establishing a direct link between OSM and our prediction model.
Thank you.
Thank you.